Okay, so let's go move on to the next part here. Okay, we're going to look at a table of a population in the United States. Okay, I don't know what year this was, probably some time ago because total population is 214 million. We know now it's probably over 300 million. So this table comes from some time ago. Okay, and also let's see, divorce rates is pretty low relative to these days. Maybe this is the 50s or something like that, right? 50s, 60s or something. Right. So let's take a look at what we're being asked to figure out from this table. Okay, first of all, we have all the males here in the top. There's 104 million males. There's 109 million females. Total population of 214 million people in the United States. And we see that 52 million of them are single. Okay, this is the breakdown by gender. 126 million are married. 14 million are widowed. 21 million are divorced. 9 million males, and 12.7 million females. So let's take a look at what kind of probabilities that we can look at here. So in this population, if I were to select a random individual, I keep saying random because later on in the semester, we're going to see that a lot of the justification that we use for using samples to represent the distribution of a population or to describe a population is that we take a completely random sample, that we don't bias the sample so that we only take, say, football games. We only sample football games where 90% of people are males, or we only sample fashion shows where 80% of people might be female or something like that. We really want to randomly sample the population here. Okay, what's the probability of being male in this population? Okay, well, that's going to be equal to the number of males in the population, which is 104.9, divided by the total population, right? Right? Not magic, just that simple. Now, what's the probability of being married in this population? Well, how many people in this population are married? 126 million. I didn't notice I didn't say male or female or whatever, just married. Okay, 126 million out of 214 is equal to 126 million out of 214 million at the time that this distribution was determined. 58% of the 59% of the population was married. Okay, what's the probability of being widowed and a male? Okay, in other words, being a male widow. Okay, well, let's see. Let's see. Here are the widows here, right? Okay, so now how many males are widowed? Well, you got 2.7 million males are widowed out of a population of 214 million. So the probability of randomly selecting one person and finding that they fit into this one box, male and widowed, out of this entire population is going to be equal to 2.7 over 214 million. It's going to be about 1%, only 1 in 100. Okay, what's the probability of being married given that you're female? Okay, let me back up to this one we just did. Probability of being widowed and male. That's the intersection, isn't that? In other words, that means that they're both male and widowed. In other words, if we drew these as two Venn diagrams, we would have one oval or circle which represents the males, right, and another circle which represents people that are widowed, and the intersection between the two of them, the people that satisfy both of these conditions would be these 2.7. They're the intersection of that diagram. Okay, so there's the intersection. Okay, let's take a look at this. Probability of being married given that you are a female. Given that. In other words, here's a phrase that tips us off that this is a conditional probability. Probability that you're married given that you're female. So we're going to say, to start off with, we're only looking at females. That's what we decided to start off with, that given that you're female. Okay, so there's 109 million females in this population. What's the probability that you're married and female? Well, married, there's 62 million married women in this population out of 109 million women. We're using 62.8 because that's the number of married women over the total population of females. Remember, that was our condition. That occurred That's why we're using 109 instead of 214. Given that the person is already, that we selected, we know they're female, what's the probability that they're also married? Okay, so now, lastly, probability of being singled or divorced. Singled or divorced, that's union, isn't it? Because either one of those two conditions. So if we had a Venn diagram here and a Venn diagram here, all those people in the two of them would satisfy that part of single, union, divorced, or single and or divorced. Okay, so let's take a look at this. These are the people that are single. These are the people that are divorced. Okay, but first, before we look at that, we're going to assume that that single individual that we took out of this population is first male. So we're only looking at the males, right? So our denominator is going to be 104.9 because given that they're male is what we're concerned with. What's the probability that they are single or divorced? So single is 29 million, divorced is 9 million out of 104 million males. So what's our probability? It's going to be equal to 29 million plus our divorced males, right, over our total population of males. Okay, there's our probability that given that a person is male, that they are single or divorced. Okay, and that's going to be 36 to 37%. Okay, it's very similar to what we did here, except here we were taught we were working with Venn diagrams. Here we were working with a table of populations. Okay, but we're really doing the same thing, and we're using the same concepts: intersection, union, and conditional probability. Okay, good. Let's move on to the next part of this. Okay, so now we're going to get into some interesting stuff. Okay, what's the probability? Let's say that we have a population where 70%, actually, this might be pretty close to what situation is in the United States right now. Let's say 70% of this population, or 0.7, proportion 0.7, is insured. Okay, what's the probability that you take three people out of the population, select them randomly, that all three of them are insured? Before we answer that question, I'm going to go down here to the situation where we flipped three coins. What's the probability that the outcomes are all heads? Okay, so let's take a look at that. Probability of the outcome. If I flip the first coin, what's the probability that it's a head? 0.5. Okay, so now let's say I flip the second coin. What's the probability that that's a head? Well, these are independent events, right? Flipping the first coin has nothing to do with flipping the second coin. It doesn't influence or whatever. So the probability of being a head is at 0.5% again. It's probably getting two heads in a row, or 1 out of 2 times 1 out of 2, which is 1 out of 4, or 0.25. When you multiply these two together, that's the multiplication rule. Okay, what about the third head? Same deal. So the probability of getting three heads in a row is equal to the probability of getting one head times the probability of getting a second head times the probability of getting a third head, which is, excuse me, equals, what did I do there? Let's see, format cells. Maybe I got something wrong with that. Let's see. Okay, let's see what this, let me try that again. Equals 0.5 times, I know what I did here. Hang on a second, times 0.5. You're probably yelling at me now, and I can feel even without looking at the question box that you guys are all screaming at me. There we go. It actually rounded it off. I'm going to go back in there and make that a third decimal place. We know that it's 1 out of 8, and 1 out of 8. That's another way of saying 1 out of 8 is 0.125. Okay. Yep. Thank you. I hit the wrong function key there. Instead of shift star, I hit command star. Okay, so that's what's the probability of all the outcomes being tails? Same thing. 0.5 times 0.5 times 0.5. You're going to get the same outcome for three tails in a row. Now, I'm going to skip this last question. I'm going to go back up here. You have a population where the probability of being insured is 0.7. Okay, 70%. you take 3 people from this population at random. What's the probability that all 3 of them are insured? Well, just like the coin, 0.5 times 0.5 times 0.5, this is going to be equal to 0.7 times 0.7 times 0.7. Since you're randomly selecting them, each selection is independent of the other selection. So 34% chance of that occurring. Okay, now here's something a little bit trickier. What's the probability that none of these people are insured? Okay, well, anybody want to hazard a guess on what that is? What's the probability that one of them is uninsured? Okay, I got a couple of 0.3s, right? Probability one of them insured is 0.3. If it's 70% chance that they're insured, that means it's 30% chance if you pick them at random that they're uninsured. So the probability that you get 3 people and all 3 of them are uninsured is going to be equal to 0.3 times 0.3 times 0.3, or about 2%, 2 or 3%. Very unlikely, because the likelihood of any individual of being uninsured is less than the likelihood of them being insured. Okay, now let's take a look at this last part that I didn't solve over here. What's the probability of 2 of the 3 outcomes on those coins being heads? Not all 3 heads, not all 3 tails, but 2 out of the 3 of them being heads. Well, that gets complicated, doesn't it? Right? The reason why it gets complicated is that the first coin could be a head or a tail. Well, based on that result, the next coin could be also a head or a tail. And the last coin could be a head or a tail, right? So I might get a head, and all 3 are going to be heads, or I might get a head, 2 tails, or I might get a tail and 2 heads, or I might get a tail, a head, and a tail. There's a lot of possibilities here, right? There's a lot of unpredictability here. It's not like before where it was so simple for us to use the multiplication rule to solve this. We're going to move on to that right now and figure out how to solve that.